also don't have any intersection of the two. So we've simplified the intensity, for lack of a better word, of the integral that we're dealing with. Now, you'll see that within each three of these, they look very, very similar. We've got 1 plus u, 1 minus u, and u. What I want to do is I want to take these two forms and I want to put it into the same form of ln of something, ln of t, which is what I'm going to use. The reason why I want to do that is because I don't want to have to evaluate three separate integrals. If I can then just have one integrand to deal with, ln of t, then I can just integrate that, and then from there I then just apply the appropriate bounds. So that's what we're going to do. You'll see that for the first integral here, we're going to let t is equal to 1 plus u, which means dt du is equal to 1, which means du is equal to dt. So du here is going to be replaced with dt, u is going to be replaced with t. We just need to modify our bounds. At u is equal to 0, we have t is equal to 1 plus 0, which is equal to 1. And then for the upper bound 1, we have t is equal to 1 plus 1, which is equal to 2. So this is going to change to 1 to 2, ln of 1 plus t dt. For the second one, we have 1 minus u is equal to t, which means dt du is equal to negative 1, which means du is equal to negative dt. So this du is going to become negative dt, 1 minus u is going to become dt, and now we just need to change our bounds. U is equal to, at u is equal to 0, we have t is equal to 1 minus 0, which is equal to 1, 1 minus 0 is 0. And then for the upper bound 1, we have, which is u is equal to 1, we have t is equal to 1 minus 1, which is equal to 0. So this is going to change from 0 to 1 to 1 to 0. Remember, this is going to be a t, and this is going to be a negative dt. So plugging that in, this was the expression that we had before, and we can see for the first one, as we just went through, remember the half is just out the front, it changes from 0 to 1 to 1 to 2 of ln of t dt, plus again 1 half out the front, changes from 0 to 1 to 1 to 0, as we covered here, of ln of t dot, I'm on the wrong line, negative dt, plus, and all I've done is just to keep it all as one same variable, instead of having u, I've just replaced it with t, and obviously everything else remains unchanged. Now, the same property that we were talking about before in terms of reversing the order of the integrals is what we are going to apply here. So for this middle one here, this negative here, is going to convert it from 1 to 0 to 0 to 1. So we then end up with this. 1 half of the integral from 1 to 2 of ln of t dt plus 1 half 0 to 1 of ln of t dt minus 0 to 1 of ln of t dt. Now you'll notice here, just let's forget about this, these are exactly the same. So we've got 1 half of an integral minus 1 full lot of an integral. So that's just equal to negative 1 half of that. And so this expression here of 3 integrals actually then gets compressed down to 2 integrals, which is great, less work. So we have 1 half from 1 to 2 of ln of t dt minus 1 half from 0 to 1 of ln of t. And then all I've done in this step is I've just taken the 1 half out the front. So we have 1 half the integral from 1 to 2 of ln of t dt minus the integral from 0 to 1 of ln of t dt. So again, although we have gone from a single integral to evaluate, we now have 2 integrals, but you can see that the complexity of these integrals have changed substantially, and we've got a very simple form. Now you may know how to integrate ln of t on its own. For those that don't, it's a very simple integral, and we're going to go through that now. Okay, so looking at the integral of ln of t dt, that's the same as the integral of ln of t times by 1 dt. Now I'm going to employ integration by parts here, and that takes the form in this example of the integral of u of t v dash of t. I'm just going to refer to it as u v dash is equal to uv, so u times by v, minus the integral of vu dash. Okay, and so the choices that we make for u of t is equal to ln of t, which means that the derivative u dash is equal to 1 over t, v dash of t is equal to 1, v of t is just equal to t, so we integrate 1, we get t. Therefore, if we plug it in, the integral of ln of t dt is equal to u times by v, so u multiplied by v, which is ln of t times by t, which is what we have here, minus the integral of vu dash, so v, remember, is equal to t, and u dash is equal to 1, so t times by 1 over t dt, which is equal to, I've just swapped this around, I just prefer to have the t at the front, but it makes no difference, t ln of t minus the integral of 1 dt. So remember, because the t's here cancel out. The integral of 1 is just equal to t, so we have t ln of t minus t plus c, and all I've done in this final step here is I have taken the t out as a common factor, and c here is just our constant of integration. Now, because we're going to be applying it in a definite integral sense, that's going to be gotten rid of, but just so you're aware for the general integral of the natural log. Okay, so now that I've got my integral for this function here in both cases, I just need to apply the bounds and we're done. So I, which equals 1/2 the integral from 1 to 2 of ln of t minus the integral from 0 to 1 of ln of t. Well, I now know what the indefinite integral is. It's t ln of t minus 1. I need to evaluate it between the bounds of 2 and 1, minus, and then to do the exact same for this integral here, the only difference being that instead of it being from 1 to 2, it's 1 to 0. Okay, so let's just plug in the bounds for the first one. So we plug in 2, so we've got 2 ln of 2 minus 1, minus, and then we put 1 in, 1 ln of 1 minus 1, which is what we have here. So we've evaluated this component here, minus, and we're going to do the same for the second. So we plug in 1 times by ln of 1 minus 1, minus, and then we've got 0 multiplied by ln of 0 minus 1. Now, I'm not going to go into a lot of detail here because I should really do a separate video, but ln of 0 is an undefined value. It has a limit. It approaches negative infinity. Thankfully, because we are multiplying by 0, it negates that. Now, saying it negates that is something I would hate for you to walk away from this tutorial and think, oh, if I ever have infinity or something that approaches infinity like that, if I multiply by 0, it's gone. That is not the case in all situations. We would actually have to evaluate this limit to show that it does equal to 0. And it's quite easy to do that, and if people are interested in that, please advise and I'll post up a video to show that. But be very cautious of that, but know in this case that yes, we can ascribe this value to be equal to 0 even though this is negative infinity. Okay, so let's just expand out all the brackets and simplify. So we have 2 times by ln of 2, which is what we've got here, 2 times by negative 1, which is negative 2, minus ln of 1, so we've got minus 1, times by ln of 1, which is what we have here, minus, so we have a negative multiplied by negative becomes a plus 1, and then for this component here, we've got minus 1 times by ln of 1, which is ln of 1, then we have a negative times by a negative again, so that becomes a positive 1, and then as I was saying before, this 0 multiplied by this component is just 0, so we've got a plus 0. So if we have a look at the components that we have, the natural log of 1 is just equal to 0, so this component here and this component here is equal to 0. You'll see here that we have minus 2, and then we have a plus 1 and a plus 1, which cancel each other out. So minus 2 plus 1 is equal to 0. So what we're left with is 2 ln of 2, which if we divide by 2, just gives us ln of 2. And so as a final result, we find that the integral from 0 to pi over 2 of sine of x times by the natural logarithm of tan of x dx is equal to ln of 2. Okay, so yes, that was a bit of a long journey. As I mentioned at the beginning, I wanted to go into a lot of detail so that people of different levels are able to see this and to be able to see the common method. But the key thing that I would like you to take from this is that the way that I looked at this integral was I went sine of x, tan of x, and I know I'm repeating myself, but just once again, and went, how can I convert that into cos? Because if I can convert it into cos, then I can get rid of having to use these sine and cos terms. And if I can do that, it means I'm just dealing with integrals that involve logs, which is what we ended up with here, and then they become much simpler to evaluate. Okay, so that's the end of the video. If you liked the video, I just ask if you could please like it. If you do like these sort of tutorial videos and you'd like to see more, please subscribe. And as with all of my other videos at the end, I take requests. So if you have an integral that you would like to have covered, please send it to me. In particular as well, if you would like it approached with a certain type of method as well, again, let me know. If I'm able to do that, I will where I can, and I will upload. Otherwise, have a great day, and I'll see you next time.